Yeah, thank you. So let's get into it. I want to talk about something called the character variety, which is an algebraic variety that we build that associated to a manifold that encodes topological information about that manifold. So I want to start, before I define or construct what the character variety is, I want to talk about an example of how this topological information can be connected to the geometric information of whatever this variety ends up being. So the manifold that we'll start with is a hyperbolic knot complement. And so we'll take in S3, we'll sort of cut out this knot and we'll get a manifold. When we build the character variety for this manifold, we know that there's a canonical component that is a curve. On the other hand, if we instead take a two-link complement, so we sort of, instead of taking one knot out of S3, we sort of link two knots together and cut both of them out of S3. That's also a manifold, and the canonical will now get a canonical component of the character variety that's a surface. So you can think of this as like the number of components of things that you're removing from S3 corresponds to the dimension of a component of this variety, which is pretty cool. So let's build this character variety for a specific example so we can see what it is. And we're going to work with the figure 8 knot. And when I take the figure 8 knot out of S3, I get a hyperbolic manifold. And to start building this character variety, I'm going to look at the fundamental group of this manifold, which is this finitely generated group. And first, I'm going to look at the SL2C representations of the fundamental group. And the first cool thing that we can see is that this set of representations actually has the structure of an algebraic variety. And we can see this pretty clearly. So any representation is going to be determined by what happens to the generators of my group. So what happens to row of A and row of B. And that's going to give me sort of 8 variables to work with. And because I have to end up in SL2C, I know that I have to satisfy these determinant conditions. So these variables have some polynomial conditions. And then I also have to maintain the relation that determines my fundamental group. So when if I send that through a representation and look at the difference of those two elements that are equal in the group, I had better get the 0 matrix. Yes?
Is that not correct? It feels like some of those unders should be overserved because that's the trefoil. You just bottom two or backwards, I think.
It's not the trefoil, it's the figure 8 knot, but I do maybe see some, I maybe drew it. I see some crossings that might be wrong.
It's the crossings, I think, where, yeah.
Yeah, it's evocative of the figure 8 knot.
That's good.
So we looked at this set of representations, and we can see that is a variety. But I want to simplify that by, instead of looking at all of the representations, I just want to look at the characters of representation. So I'm going to look at this set that instead considers only considers the trace of the matrices that I get from my representations. And it's a nice fact that for any representation of my fundamental group, the character chi rho can be found using only 2 pieces of information. And that's the character of A and the character of A times B, where A and B are the generators of my group. And I'm going to give those 2 pieces of information variable names Y and Z. And if I use the relations, all the relations that defined that set of representations, the representation variety, as well as the relations that defined that would define chi rho of A and chi rho of AB, I can use kind of all of those polynomials, all those relations, to construct a variety that matches up with my set of characters. And this is what I'm going to call the character variety. And in this case, where we're looking at the figure 8 knot, we got just a single expression that defines the variety, and it's this nice polynomial, which is a smooth plane cubic, which means that the character variety of the figure 8 knot is an elliptic curve, which is a really pleasing result. And so we can do this construction for any knot or link complement. In most cases, we're not going to get something as pretty as this, but there's a lot of questions that we can ask about this. So my research is to compute the character varieties, not of knots, but of hyperbolic 2 links. And as I said at the beginning, if I do that, instead of getting a curve, I'm going to get a surface as a component of my character variety. And I want to explore the geometry of those surfaces. So some questions I could ask are, what types of surfaces even can arise as components of these character varieties? So like in the Kodaira-Enriquez classification, can I get like any one of those surfaces? That's unknown. If I have a specific surface, can I find rational points on it? And can I find integral points on it? And I would love to study the Brouwer class of these surfaces. And especially the last 2 questions, those are known to carry topological information in other examples. So it would be really nice to find examples of, to find new examples that I can study those for. Thank you.